I'd like to basically say welcome to everybody. This is a webinar series brought to you by Northwest Net Zero Hub with Stiebel Eltron, who'll be doing the bulk of the presentation. My name is John Mullins. I'm the Estate Decarbonisation Lead at the Northwest Net Zero Hub, with Namitha as my trusty aide, who's actually done a lot of the legwork in the background to make this event happen. The hub, as you see, it's at the centre of trying to bring free support to local authorities. We're funded by DESNZ. The Liverpool City Region Combined Authority hosts us, and that's why you'll have seen some of the emails coming from Mersey Travel and things like that, because they're kind enough to give us space to live. But our basic aim is to provide free technical support across the entire energy transition spectrum. So anybody who's looking for technical advice on how, in terms of strategy work, planning work, or delivery work, we're here to provide that free support. This is one of those elements of support, and this is providing knowledge, education, training around heat pumps. And it's such a big topic, we've broken it down into 5 parts, and really it's intended for US public sector members. It's basically going to look at, how do heat pumps work? How do we apply them? How do we maintain? How do we operate? So there's a rounded understanding of heat pumps. As we go forwards, we'll be sending out the registration links for those sessions, and for each one, please register, book in, and the program should hang together nicely. Matt Fitzpatrick from Stiebel Eltron is going to lead us through the technicals here. Stiebel Eltron, lots of experience. It's a 100-year-old company. They've got a UK base here in Bromborough, very close to our offices, and they've got 50 years of experience in putting heat pumps together and working in the market. The UK is a long way behind places like Germany, so it's good to learn how these things operate. They're not new technology. It's old technology. It's just new to us. Matthew himself, he's the regional specification manager for renewables, and his bulk of his experience with Stiebel Eltron has been around both teaching heat pump technologies as well as looking at specifying, fitting, and operating them. So without me taking any more time up, we've got roughly half of our time on a presentation and half of our time on Q&A, which I think is where we'll get to the meat of what you guys are interested in. Let me hand over to Matt. So Matt, all yours.
Thank you very much for the introductions. So this is the first segment, and we're going to look at how a heat pump works. There are some of the notes or subjects we'll cover during this webinar, which will focus on what it's like to live with a heat pump, noise levels, and a brief look at planning and requirements. So first of all, how does a heat pump work? So heat pumps can take the energy from the environment around us. This is done by the refrigeration circuit. As John mentioned, this isn't new technology. It's technology that's been in use for over 50 years, and we actually have something very, very similar in our homes. It's a fridge freezer, and it works in the same process. So we have 2 types of heat pumps. We have an air source heat pump, which will collect the energy from the air around the unit, and we have a ground source heat pump, which collects energy from the ground. Now, this is all done using refrigerant gas, and refrigerant gas can still collect the energy from the air or the ground in temperatures as low as minus 20 degrees. The easiest way to explain refrigerants is what I call the ice cube analogy. Ice melts at 1 or 2 degrees. If you place an ice cube on your hand, it will melt, and there is very little input that you need to do. It's just your body temperature, 37, 38 degrees, melting the ice cube. And this is how the heat pump and refrigeration system works. It collects as much energy without any electrical input as possible. The only electrical input we have is from the compressor, and that will slightly increase the output and performance and transfer the energy from the air or the ground through the refrigeration circuit into our hot water cylinders or our heating. The reason heat pumps are a lot more efficient than other heat sources is quite simply, if we go back to the ice cube theory, it takes very minimal effort, very minimal energy to place the ice cube in the palm of your hand. The natural temperature we have in our body heats the ice cube. We do not need to move. We do not need to exert any force. If we were to place the ice cube in a pan of boiling water, it would melt relatively quickly, but we have to add additional energy. We have to force that cycle a lot quicker than what we can do naturally. So that's how we can see heat pumps being 300, 400, in some cases 500% efficient, because we've collected so much energy from the environment around us, only using a minimal input of electrical supply and load for the compressor to move the energy from the air, from the ground, into our homes through the heating systems and domestic hot water. Now, there's a conversation about refrigerant gases. These are ever changing. We are trying to get to the lowest GWP or global warming potential to reduce the impact to the ozone layer. At the moment, we are using R290, which is a propane-based refrigerant. There are others such as R454C. These can still deliver relatively high temperatures, so 75 degrees. So very, very low GWP, very, very good for the environment, moving away from the older refrigerants. So they are future-proofed. So what we can do, we can take the 10-degree air temperature, transfer the energy through the refrigeration circuit, and we compress it. So a bit like a bicycle pump. If anyone rides a bicycle, if you were to pump your tire up, you will feel the hose and the nozzle get increasingly hot. That's because we put it under pressure. And that additional pressure through the compressor allows us to transfer the additional heat into effectively what we call a plate heat exchanger, which allows the energy to transfer through two different circuits. And then we can send up to 75 degrees into our radiators or underfloor or into our domestic hot water cylinder. As we've said, this technology is tried and tested. We have some fantastic photos among other manufacturers of heat pumps in Sweden and Finland with 3 foot of snow, and the heat pumps are still thundering along quite happily, keeping these homes warm and comfortable. So the different types of heat pumps we have, as I've mentioned, is air and ground. So from an installation point of view, air source is a lot easier than ground source. It can be placed in a variety of areas. It could be outside the property, it can be on roofs, it could be close to the property, or it could be 15, 20 meters away. Because it's collecting the air around the heat pump and using the energy there, it's quite versatile. It's quite quick to install, and it's relatively easy to maintain and service. With ground source, there is 2 different approaches. We can lay ground collectors, effectively it's loops in a field that collect the energy from the ground through a hydraulic system, so a wet system filled with glycol, and take that back to the heat pump, and that becomes its energy source. With ground source, you will normally find these in larger properties, commercial buildings, or areas where there is large amounts of land. When we look at efficiencies, as technology has caught up, air source and ground source probably have a 5 to 10% difference. Ground source is 5 to 10% more efficient. And this is simply because the ground temperature doesn't vary. If you dig a trench that's 1.5 meters down into the ground, and you were to stand in the trench when it's freezing temperatures, you would be warmer underground, effectively in the trench, than you would be stood on top of the ground. This is all to do with solar thermal energy. So the sun comes out in summer, hopefully if you have a good British summer, and it heats the ground and it becomes a large thermal battery. And that energy is then reserved for winter. In the way of installation costs, air source is more cost effective. You haven't got the additional groundworks. But as the technology is caught up, they are almost on par for efficiencies. So you can see 400 to 500% efficiencies. And what this means for either air source or ground source is if we were to spend 1 kilowatt of energy, for example, at 24 pence per kilowatt, the heat pump can deliver 5 kilowatts of energy into the property at the cost of 24 pence. Whereas our fossil fuel systems at the moment can range from between 80 to 90% efficient. So you're not getting that full 9 pence per kilowatt. You're not getting that full kilowatt. You're only receiving 80 or 90% or 8 or 900 watts. There are other types of collectors that you can use for ground source. You might have heard the term boreholes or vertical collectors. This is where they will drill a vertical hole into the ground and place a closed pipe. This allows you to collect the energy in smaller squared areas and still have the use of a ground source heat pump. So you may find if, for example, you had a building with a car park and the area wasn't big enough to have horizontal collectors going across, you can use boreholes and go down in a smaller area and then still use ground source. Interestingly enough, we can also use open water sources, lakes, rivers, the sea. It depends on the equipment because obviously there's salt water. But the higher the ground or source temperature, the higher the efficiency. So a ground source heat pump might be 450% efficient with 6 degrees on horizontal collectors. But if it's open water source, so it could be an open lake, and the water temperature on average 12 degrees, it may now be 575% efficient because we have more energy from the environment that we can collect. And that's the key. The more we can take out of the environment, the less we have to spend electrically through the grid effectively. So we've discussed the heat pumps themselves. This is just a brief look at what you can use in the system. So it ranges again on a type of property. If you had a 2-bedroom terrace property, as you can imagine, the equipment required will be a lot smaller than an office building that has 150 people in there from 9 to 5. So what the heat pumps can achieve, they can easily heat domestic hot water up to 50 degrees. There's a Legionella cycle or a pasteurization cycle, which kills any bacteria in the cylinder, which occurs once a week. And with these higher flow temperatures, the heat pump can achieve that using the refrigeration circuit. Normally, you may find an electric immersion completing this task. However, with an electric immersion, it's what I say is 1 for 1. So for every 1 kilowatt you spend, that is what's delivered through the immersion. So even if the heat pump is 250% efficient, on the last 5 or 6 degrees to reach that 60-degree temperature required in the cylinder, we are 150% more efficient than using an electric immersion. We can achieve comfortable room temperatures because the idea behind a heat pump and its operation is to run low and slow, as I call it. It's constantly topping up the heat loss or the energy loss through the building. And because we're only delivering at low flow temperatures, 38 to 50 or 45 degrees, we're not overworking the unit. It's not switching on or off. It's just almost cruise control. It's modulating to assess and provide exactly what the building needs. In a way of being comfortable, this means you won't feel any drafts or temperature fluctuations. It's quite interesting. The human body only needs a 3-degree fluctuation in temperature to go from increasingly or uncomfortably warm to uncomfortably cold. And if we think about that, in the UK, we have a wide range of temperatures. At the moment, it's around 18, 16, 15 degrees outside. People may find it comfortable. But if it drops to 12 degrees, people will then feel too cold. Or if it gets to 22, people feel too warm. And this is how we look at the rooms in our homes and our properties. We keep it at a steady 20, 21, or 19 degrees, and it becomes very, very comfortable. We can also ensure that we can produce enough hot water. So this is all done through what we call mixed water volume. So we no longer need 500-600 litre cylinders. We can have 200-300 litre cylinders for smaller properties and larger for big commercial buildings. Because when we look at the amount of water and temperature that we actually need, we can blend it down. So for example, you may store a cylinder at 60 degrees, but if you went to wash the dishes and you turned on a tap and 60-degree water was coming out of the tap into the sink, the moment you put your hands in the sink, you will instantly need to add cold water because it's too warm for our bodies to take. So we naturally blend it down to around 40 to 45 degrees, which is a comfortable temperature. So in that scenario, If we held the cylinder at 50 degrees, we can save energy on save energy rather than trying to ramp it up those extra 10 degrees. We add cold water, blend it down to 45. We only use what we need. So plant rooms, it's always a big discussion. And when we look at heat pumps and system design, in some cases, it's not as easy as just remove the gas combi boiler off the wall and place a heat pump outside. There's some things that we need to do. So we will call them plant rooms or technical rooms. In reality, in the UK, we have a variety of homes built from the 1800s to modern day new build properties. And we have a variety of areas that we can use. So we need to create and utilize specific products. So there'll be pre-plumbed cylinders, which are available on the market, as we can see on the screen. This houses all of the controls, circulation pumps, cylinders, everything the system requires. And these vary. You can have separate cylinders. You can also have huge technical rooms with all the space in the world. So when you're looking at a system, especially for heat pumps, you'll need to ensure that you have a suitably sized domestic hot water cylinder, and in some cases, what's called a buffer cylinder. This is a volume of water, it's a tank, a cylinder, that is used for the heating system, so radiators and underfloor. In some pre-plumbed cylinders, it's all included, and you can have it separately. So we need to have a look and understand what space we can utilise. Installation times are a little bit longer than combi boiler systems because there's pipe work, there may be upgrades that need to be done for the retrofit market. For example, radiators that might use microbore, very thin internal diameter bore pipe work may need to be upgraded. I normally say a heat pump system can be installed between 3 and 5 days, give or take. So living with a heat pump. We utilise something called weather compensation. And the idea behind this is if it's 16 degrees outside and we need to add a small amount of temperature into our homes, into our properties to bring the room temperature up to 21 degrees, we do not need the heat pump running flat out 100%. It could run at 30% or 40%, again, becoming more efficient. So the weather compensation system looks at the outdoor temperature, it looks at the room temperature required, and it also looks at what we call a heat curve. And this just means how much temperature we need in X amount of degrees outside. As you can imagine, the colder it gets outside, the higher the temperature we need. And this automates the heat pump cycle. There's no longer the process of, oh, it's a bit chilly in September, should I switch the heating on? Or actually it's March, I know I shouldn't have the heating on, but we've had a really, really cold day. The heat pump does this automatically. So it will add enough energy as and when it needs. They're very, very clever systems. As I said before, they can modulate down and they will be able to deliver exactly the correct amount of energy a property needs. In the UK, we've got to specify a heat pump to the design temperature for the property and the area. So for the Wirral and Liverpool, it's -3. So we need to make sure the heat pump at -3 can deliver the exact amount of energy that property needs. In reality, most homes only need around 7 to 9 kilowatts. When we look at the average heating season temperature in the UK, especially for the Wirral and Liverpool, we see 14 hours at design temperature, which is -3 or -3.2 to be exact. The remainder of the season is 2,500 hours between 5 and 10 degrees. So we need our heat pumps, or heat pumps I should say, to modulate all the way down. So if we need 7 kilowatts at the coldest points, the heat pump should modulate to 3.5 for those 2,500 hours. And that's how they become efficient and provide that comfortable temperature. The other thing to bear in mind is there's a myth heat pumps are loud. They're not. Those are the old days. They've disappeared. With this inverter driven system that we see now and the modern technology, we have heat pumps that are quieter than kitchen microwaves. The one on the screen is 46 decibels. A kitchen microwave is 52. Heat pumps are no longer intrusive in the way of sound or noise to neighbours or properties adjacent or near the project. As technology's moved on, you can control heat pumps through apps. There are web service portals where you can remotely access the heat pump. You can complete diagnostics. You can almost, I'd say, complete a service, 60% of a service online. You can monitor faults. You can pretty much see a system has a problem before it's even gone cold. which means it's proactive maintenance, it's proactive repair, it's proactive peace of mind. There's built-in heat metering on most heat pump systems. This means we can see how much energy has been used and how much energy has been delivered to the property. So you can actually determine using a smart meter and the built-in energy monitoring how much the heat pump has cost to run. Temperatures and time programs can be adjusted remotely through online services. There is the controller as well, which is simplified for consumers, and the engineer's menu is normally locked, so people can't fiddle or change parameters. But if they can, online services can normally go in and backdate it to what it previously was. So cost comparisons. Everyone always asks, what's the repayback time, or how much will I save? Well, there's two aspects. In this property or this example, we can save 30% compared to fossil fuel heating. And this is just in the first year. So it will cost I think it was around a 6 kilowatt system. The property needs 6 kilowatts, £521 per year for the heat pump to run. With gas, it's 951, and oil, which is quite expensive, is over £1,000. It does bring the cost down a lot. So especially in modern climates, fuel poverty, energy prices rising, things like this, it provides that level of security. You can integrate solar PV into the systems, and this has two benefits. In the autumn and spring months, you can offset your load, effectively your costs. In the winter, it can still allow some energy to be delivered and provided to the air source heat pump, again to offset costs. Then interestingly enough, as we build more new homes, we insulate them to the best that we physically can. We have a heat wave, and then properties overheat. It becomes very uncomfortable. We can see that with the overheat part of the building regs. Heat pumps can cool properties as well. They can be done through fan coils or underfloor heating, underfloor cooling. And I normally say, if you have solar PV and we have a fantastic, lovely sunny week where there's a heat wave and it's collecting all the energy through the panels, we can place the energy somewhere useful. We can send it through the grid. We can reheat domestic hot water cylinders. We can charge EV cars. But what about the heat pump? Well, we can ask the heat pump to cool the property using the free energy that we've gained from the solar PV. An example I use for a 7 kilowatt home with heating, cooling and hot water for 200 hours in the summer period to operate in cooling would cost £120. So that's worked out at 24 pence per kilowatt. If you have solar PV, there is a good chance that you're cooling your property for free, or if not free, small amounts compared to that initial figure. And as well, we look at the initial running cost here on the cost comparison. The one thing we forget is if gas is only required for the heating system in a home or a property, and you have electric cooker, electric hob, everything else is electric. Once the gas service is removed, there's an instant saving on standard charge as well. So that can be added on to the cost saving. Then we look at the kilograms of CO2 saved per year. So a heat pump, same system, 6 kilowatts property with one of our heat pumps. So the prime energy usage is 4,259 kilowatt hours per year. What I can see, sorry. Try and zoom in. And primary for gas is 13,753. So the heat pump already is using 4 times less in the way of energy. And at the bottom, we can look at the CO2, kilograms of CO2. The heat pump is under 1,000 kilograms of CO2, whereas gas is 2.5 times that amount. So there's a big saving there as well. So the big question, is my heat pump suitable for, is my home suitable for the heat pump? Yes. Yes, over the years, people worry about insulating and we have a fabric first approach, but in reality, there's two approaches. Fabric first is great. It's the best way to do things. But from that as well, most modern homes or most homes now have double glazed windows and doors, loft insulation, chimneys blocked up, levels of ventilation in there that's brought the heat loss down. it means they are suitable for heat pumps. Anything we add on is a bonus because the heat pumps can modulate down. So how we heat the home, there's two options. We can use underfloor heating. There are overlay systems that can be laid on suspended floors and concrete screeds, and there's radiators. Most companies or underfloor designers will design the underfloor system to work with the lower flow temperatures for a heat pump. We can use temperatures between 25 and 35 degrees to sufficiently heat a home. For radiators, we can still heat through radiators. Now, there's two theories and thought processes behind this. I always say, if it's possible, oversize the radiators. So that could be increasing its length and width to provide the correct heat output, or changing to K3 radiators, so wider radiators. The other aspect as well is with new refrigerants, so for example R290, they are very, very efficient at higher flow temperatures. So if this is a two-stage or two-phase process or project, you could install a heat pump and the system and run at slightly higher flow temperatures and initially sacrifice some efficiency. But then phase two is adaptations and changes to radiators or underfloor, which would then increase the efficiency. So it means we don't have to rule out properties and say, oh, sorry, that's not feasible, that's not suitable for an air source or ground source heat pump. I would say 95 to 97% in the UK are ready, to go for air source and ground source heat pumps. The key point I always stress is the lower the flow temperature, the better the efficiency. So if you imagine driving your car, if you sit on the motorway, inside lane, cruise control, 58 miles per hour, you will get a fantastic MPG compared to sitting in the outside lane, overtaking loads of cars, speeding up, slowing down. We get there at the same time, the same rate. One is less efficient, which is the outside lane in and out of traffic, compared to the inside lane of the motorway at cruise control. It's slow and steady. So, key points to take away from, is my home suitable for heat pumps? As I've said, most of the homes in the UK are ready, and this depends on size and levels of insulation. We can cascade heat pumps. So if your property, or if the property needed 30 kilowatts, we could add two 15 kilowatt heat pumps to cover that load. So that can be done. Cascade systems are quite common in large properties, buildings, or older properties that might be grade listed. Heat loss can always be reduced. This is the point I was stressing before about fabric first. So fabric first is great, but we can still offset that carbon offset and running cost as well by adding insulation afterwards. So it could be external wall insulation, it could be suspended floor being insulated. We can always add afterwards. It will only benefit the heat pump and benefit the property. Over the years, the thermal insulation and the levels that we have improved dramatically. So the smallest impact that we do with insulation has a massive difference on the home or the property. I've just got a little bit about funding. Thought it was quite interesting in the way that there's always been a push, and there's a bigger push now with the buzz scheme, boiler upgrade scheme being increased and extended. Even heard that on a radio station as I was travelling up and down the West Midlands yesterday, which I thought was fantastic. So there's lots of funding available for consumers as well. So there's a really big push in the industry at the moment for heat pumps and renewable technology. So there is permitted planning rights for air source heat pumps. To run through a couple of key points, they must have a noise level at or below, I think it's around 42 decibels at a set distance. In Scotland and England, they must be installed at least 1 metre away from the property boundary. In Wales, it's close to 2 or 3 metres. It must be for heating purposes only. Can't be installed on a pitched roof. You can install them on flat roofs, but it has to be at least 1 metre away from the edge of that roof. And the air source heat pump must not be installed on a wall if the wall fronts a highway or is visible from the road. As well as that, it can only be 1 unit for permitted planning at the moment. So this is all to do with square meterage and compressor sizes. For ground source heat pumps, it's relatively the same. So for ground source, you can only use 0.5 hectares for permitted planning and development rights. So that's the total excavation is 0.5 hectares. Ground source heat pumps, they're normally installed inside the property, so being able to be seen from the road, etc., the highways, doesn't really matter with ground source. There are some regulations and information about installing grade listed buildings. It can be done. We have done quite a few over the years. There are covers that you can get for the air source heat pumps to hide them so they're not on show. They can be vinyl wrapped to match the brickwork of the building. If it's ground source, which is normally more favoured, they are in a plant room or a purpose-built room, and there's nothing to be seen in the way of a ground source heat pump system. Designs are always a crucial thing for renewable technology and air source heat pumps and ground source heat pumps. Most manufacturers can normally offer help with planning. We have our own planning team as well, so we can cover that and we can design the system. And the idea behind that is to be able to create the right product or the right kit list for the property, make sure everything's been accounted for. I always say if you're looking to install an air source or ground source heat pump, initially you need a site visit. Go and have a look at where it's going to be housed, installed, have a look at the property. If it's ground source, see how much land is available. If it's air source, look for locations. Is it going to be obstructed by anything? What heating system have they got currently? Is there any upgrades to the pipework, the flow and returns to the radiators? Are they adding anything to the property, an extension? Because that will increase the heat loss. Have a look at the heat emitters, the radiators and on the floor, and check the sizing, see if they are suitable. I don't normally use rule of thumb, but as an example, radiators, I say it's 1.5 times the size of what they currently have. Are they looking to cool? So is it a new build property? Will they be cooling in summer rather than just a heating only system? If so, that'll require a different design. And control systems, is it room thermostats? Is it individual room control? Normally, you'll then have a hydraulic and electrical diagram that's been prepared to help installation team to be able to install the heat pumps. There'll be commissioning parameters provided as well. So it'll be commissioned as per manufacturer specification, and normally there's assistance there as well. So the stages I've just put into 6 steps: inspect the plans, an initial site visit, feasibility study, will it work? Is it capable of handling the property load? And will it be used correctly? Installation, an installation quote, look at materials that are required, upgrading radiators, underfloor, etc. Design a system, planning applications, and then DNO requests. The DNO is the Energy Ofgem network. Effectively, when you apply for a heat pump, it has to go through the DNO energy network to make sure the load to the property is suitable. Most of them on the DNO website now, which makes it a lot easier. And then the 6th step is install the heat pump. So overran slightly, so I do apologise, but we have about 20 minutes for questions.
Thanks, Matt. No, that was really good. See, there's a couple of questions already on the chat, and I think to everybody, if you've got questions, drop them into chat, and we can pick them up. Question here is, what are the average fault rates in heat pump types in comparison to boiler types, and repair costs compared to a gas boiler? So how frequently do these things break down, and how expensive is it to fix them?
Okay, I can only say this from our aspect, because I don't deal with other manufacturers. The failure rate is relatively low. And to explain that, the compressor is our compressors are rated for 35 to 40,000 run hours, which you're talking probably 15 to 20 years life expectancy quite easily. Circulation pumps, again, when they're in use, quite a robust component. The failure rates are relatively low. What I normally say is it's not a failure rate or a problem. It might be the system's lost pressure. So the heat pump generates a fault code to say, help, something's not right, there's a high pressure fault. And then when we log into our online monitoring, we can see the system pressure in the radiators is exceptionally low. So then we could call a customer or the service engineer and say, could you increase the pressure? It could be that it's not serviced correctly and leaves build up and it can't defrost, it can't clear any water that's built up in the winter seasons. Again, easily rectified with a service. It's a very, very low failure rate from our point of view. The online monitoring helps. That doesn't mean things don't fail, because they do. You know, everything in the world can and will at some point break. I would probably say pumps, again, moving parts, submerged in water at all times with a variety of water qualities across the UK, would be a part that may need to be replaced. As an example, I have a customer who has 23-year-old units in student accommodation, and I occasionally get a phone call from him saying, can I have 2 circulation pumps, please? The heat pumps are just carried on quite happy for 23 years. They are a long life product in a nice way. As for boiler types, there's a lot more that can go wrong with boilers. You know, there's more moving parts. Our refrigeration system is sealed completely, so it never needs to be opened or serviced, just like a fridge freezer. Again, how often do we swap fridge freezers in the UK? Unless we're getting a kitchen refit, very, very rarely. So they are quite robust, very, very low failure rates, very easy to service. They're almost fit and forget, and I don't like using that term, but yeah, with the online support. Yeah.
So Matt, can I ask you, you know, when you have a gas boiler, you also then have an annual gas service that's sort of required. You get your Corgi check or whoever it is that comes in and checks off the gas boiler. Is that required for a heat pump?
For the warranty,
what do we need
yes.
to do?
So for the warranty, it will be required, and it's quite simply for an air source. It's clean the leaves and debris up the back, check the system pressure, check the water quality, run the heat pump to its Legionella cycle for hot water, so 60 degrees, and mark down the refrigeration data so we can assess the refrigeration circuit. And then the same in heating, G3 checks, so expansion vessel, pressure relief valves, and that's it. To be honest, that's all there really is with a heat pump service. It probably takes about an hour on site, hour and a half, give or take.
One of the questions there is around what is the cost of a service? And if it's an hour and a half, I see the cost that somebody's been given is £400, which seems a little excessive.
Okay, so installers' prices will vary for servicing. So some may charge £400. It depends what area in the country you're in. So in London, you might see a higher charge because of parking, travel times, etc. It may be around £200 to £250. It also depends on the size of the installation company. If you imagine you've got a plumber or 2 plumbers, and it's a one-man team, and they've got to install heat pumps and service them, there might be a higher cost because they're coming away from their steady stream of installation work to service. If it's a bigger company, then they will have a designated service team. If you have maintenance engineers, then we can educate them and train them on how to service the heat pumps. So that becomes an internal cost in a way. But it does vary. I mean, we offer servicing, but that is the full package. So manufacturers can offer it as well. £400 though does seem a bit steep, personally.
And is it, you know, there was lots of controversy in the auto sector where you could only get your car serviced with through the dealer network. And then it was a case of, no, actually, anybody who's skilled and trained and competent can do the servicing. So do you have to get a heat pump serviced by the manufacturer, or is there a quality assurance process where you could get anybody, you know, like if I need my gas boiler servicing, I can go to any gas certified fitter to come along and do the servicing. I don't have to go back to a Valiant provider to do the servicing. What's the situation with heat pumps?
Any plumber can do the service. We have an easy to follow service sheet. We offer training as long as they have a G3 accreditation, which most plumbers do, then they can service a heat pump. So, yeah.
Okay. Looking at questions, we've got a question here. Would you recommend a towel type radiator with an air source heat pump in a wet room?
That's a very, very good question. Brilliant question, actually. So, yes, you can use tile radiators. You can see there's a however coming here. However, because they heat during the winter, we would say install a dual fuel tile radiator, so one with an electric element, and you can switch it on and off. That is the best solution. If someone wanted just a tile radiator on their own, I would advise it will be warm in winter and cool in summer. That's it. What can be done.
Yep, that's fair. Query on cooling wise. So there's this. We'll combine these two questions. There's, you mentioned there that we insulate our houses, then we've got to pay money to cool them. Or why don't we just not insulate them as well, and that way they cool down a little better. The other one would be, can you cool with an air to water heat pump, or can you only cool if you've got an air to air heat pump? And maybe you want to touch on the difference in those technologies.
Yes. So insulation, very good theory, but it would cost us more to heat the home in winter than it would to cool in summer. The cooling in summer is more of a luxury perk, is the nice enough way. It's like when you go to the cinema and you can opt for a normal seat or the VIP. Going to the VIP in the top, that's cooling. It does have its major benefits, and it's only a fraction of the cost. The air-to-air and air-to-water system, air-to-air isn't as efficient, especially with properties. If we heat the air temperature, the air can leak through gaps and holes in properties. It doesn't hold the temperature as well. It can move away quite quickly, so you'll spend a lot of time trying to heat the air, which means the room or the area may feel warm, but the fabric of the building's cold to touch. So the walls, which can then lead to damp, mold, mildew, a lot more problems there. Air to water, water has a better density and thermal property than air. So we can load the energy into the volume of water, circulate that around the property, so through underfloor or through radiators. And as that heat is coming off the heat sources or the heat emitters, that's transferring through to the air temperature, the fabric of the property, the walls, the windows, the roof. And then we effectively live in a storage heater in a roundabout way. All the bricks are warm and they're radiating heat back in. Our low temperature heat sources delivering comfortable temperature as well. So yes, air to air exists. It's like the older technology. It works, but it's not the most efficient. And then cooling through an air to water system, it's the reverse. If you imagine the sun is beaming down on a brick wall and it's transferring all this solar energy, and that wall is heating up and it becomes a big thermal mass, just like a storage heater. As we send 16, 17 degree flow temperature through the underfloor, heat naturally goes to the cool area. So the heat will rush from that warm wall to the floor, so the screed. You may have 27 to 30 degrees on the brick wall, even higher in some cases. There's a huge differential between the 17 degrees in the underfloor and the 35 degrees on the brick wall in the temperature. So it's pulling the heat away very quickly, which then cools the fabric, and it feels a lot cooler in the room. It's like going to a supermarket and walking into the fruit and veg aisle. It's a nice, passive, cool zone. But bear in mind, when we touch a brick wall in summer and we go, oh, that's hot. If something is 38 degrees and we touch it, we don't feel a massive difference. So if we feel 40 degrees in the brickwork, that's really warm. It's transmitting into the property.
Okay, that's good. A question on phase change materials. So you've mentioned about using a heat pump to store water. But if we use a phase change store, and maybe you want to touch on phase change, do we still need the Legionella 60-degree cycle?
No, we don't. It's classed as instantaneous. So if there's a small volume of water that isn't stored, then we do not need to complete a Legionella cycle. It's only stored static water. So the phase change material, you do not need to run a 60-degree cycle. However, the phase change material needs higher temperatures. One of our heat pumps can be used with a phase change material storage system, but it requires between 65 and 75 degree flow temperatures to produce that hot water. Again, it's going back to that efficiency. We could be 300, 400% efficient on hot water for the majority of the cycle using a cylinder, but then less efficient on a phase change material. But it depends how much it's going to be used. When we talk about planning, that's the sit down, dark room, we crunch some numbers and go, okay, this is a better solution. But it can be done, and you don't need to run a Legionella cycle.
Okay. And then are there any benefits of a split system over a monoblock? Now, I must confess, I don't know the meaning of that question, so I will leave you to answer that. That sounds
okay.
That's beyond me slightly.
So a split system, just to explain to everyone, is if you imagine we have the outdoor unit 10 meters away from the property, and then a cylinder inside. The connecting pipework we have isn't filled with water, it's filled with refrigerants. So we have a greater mass or greater volume of refrigerant. This means you cannot have any plumber install this system. It has to be an accredited F-gas engineer, refrigerant engineer. This also means if there's any leaks, then rather than the F-gas engineer assessing a small monoblock unit outside where it's all contained, he's traveling a 20-meter distance to leak test and check and repair. It does cost more. The monoblock system is easy, it's maintenance free. It could be fitted and by any plumber effectively, whereas the other system needs an F-gas engineer, so there's higher costs for repair. Split systems aren't as common in the UK anymore. We normally stick to monoblock, and we just increase the size of the heat pump as and when we need, because a refrigeration system shouldn't be opened unless there's a fault. And when it is opened, it's a lengthy process to vacuum all of the refrigerant out, flush it and test it and replace components, and then fill it back up again and cycle it through. It could take 4 hours, 5 hours for a small system, depending if the heat pump isn't being stubborn on that day. So split systems, I'd probably go for a monoblock over a split, just for simplicity, ease of installation, and the cost effectively.
Okay, and then might be the last question at the moment. What would you suggest for terrace properties with a small amount of space outside? What do we do if we're space constrained? And I think I'll expand the question: space outside and space inside, because we see these pump rooms with
Yes.
large tanks. How do people actually address that? And then while you're answering that, I'm going to put 2 links onto the chat for people. One is the Energy Systems Catapult guidance on heat pumps, and the other one is a rather good overview on heat pumps from the Guardian newspaper with a rather nice interactive graphic on how heat pumps work. And then I'm going to hand back to Matt to answer this. What do you do for a small terraced property?
Interestingly enough, I'm doing an eco conversion on a terrace property at the moment, and I have enough space outside for a heat pump. And just to express, I have a 24 kilowatt combi boiler installed at the moment. I know I shouldn't say it, that's why I'm moving to a heat pump. However, I have completed a heat loss calculation on my property, and for heating, I need 5.6 kilowatts. So almost 5 times less than what my combi boiler has. So there's space outside. Heat pumps can be mounted on the walls, on legs. Depending on the model, they may only require 1 meter in front. They may require 2. They are relatively small. So there's different ways that it can be installed. The meter boundary, what you'll find with most terrace properties is at the back, it can be installed centrally. So you've got the clearance either side. As for the plant room or the tank, this is where pre-plumbed cylinders come into play. They can be fitted underneath the staircase. They could go in cylinder cupboards. You can also do something called the bufferless system. Now, a bufferless system doesn't have a buffer cylinder for the heating. It's just running constantly through the radiators, and you might have a small 20-litre, what we call volumizer on the system for defrost cycles. So it can be done. You'll probably find a 2-bed terrace property only requires 200 litres of hot water, maybe 180. And we'll have 5 to 6 radiators, maybe with a towel radiator in there as well. So a small volumizer. Underneath the stairs is a good solution. You can get horizontal cylinders that go in the loft. And you can also get small stainless steel cylinders that can go in the loft as well. Depending on the age of the property, if it's 1900s, then loft space can be difficult. If it's more modern, you might have some more access as well. So yes, you'd be amazed how small of a heat pump and cylinder is actually required for a terrace property.
There was a question from Chris earlier, which is around, does Stiebel Eltron offer a heat pump powered cylinder, or do you guys just supply the heat pumps?
We do have a heat pump powered cylinder for domestic hot water. It's 300 litres and it goes inside the property. So if you have a warm room, kitchen, storage room, utility room, it will go into that room. It only takes a couple of degrees out the air temperature for a hot water cycle. So it might take you from 21 to 18, and then you have 300 litres of hot water.
Okay, we're coming to the top of the hour. Matt, can I say thank you very much for the presentation? As said, it's all part of a series. So this was really the introduction. And then as we go through the coming weeks, we'll dive into each of the topics in a bit more depth.